Hello, my friends. Today we are going to work with the Bayesian calculator and the contingency table. To do that, we will take a problem that we find in the book OpenIntro Statistics in page 98, written by D.S. David, Christopher Barr, and Mina Chetinkaya-Rundle. And it says, in Canada, about 0.35% of women over 40 will develop breast cancer in any given year. A common screening test for cancer is the mammogram, but this test is not perfect. In about 11% of the patients with breast cancer, the test gives a false negative. It indicates the woman does not have breast cancer when she does have breast cancer. Similarly, the test gives a false positive in 7% of the patients who do not have breast cancer. It indicates these patients have breast cancer when they actually do not. If we tested a random woman over 40 for the breast cancer using a mammogram and the test came back positive, that is, the test suggested the patient has cancer, what is the probability that the patient actually has breast cancer? We could also interpret that as the probability of H given D. We have another valuable information in the problem that says, notice that we are giving sufficient information to quickly compute the probability of testing positive if a woman has breast cancer. 1 minus 0.11 equals 0.89. Now, we see that the information that we can identify in the problem is enlightened in red. About 0.35% of women will develop breast cancer. In about 11% of the patient with breast cancer, the test gives a false negative. And the test gives a false positive in 7% of the patients who do not have breast cancer. This information is valuable to fill out our contingency table. This is the contingency table that we are going to use. For us, the D will represent a mammogram test given positive, and the D primer will represent a mammogram test that gives negative. Breast cancer will be represented by H, and no breast cancer will be represented by H primer. Okay, so using the conditional probability, we can fill out the spaces in our matrix. For example, the probability of D given H equals the joint probability of D and H divided by the probability of H. Now, we don't have originally the joint probability of D and H, but we can calculate it by doing some math. That means this is our X, and the result is the probability of D and H equals 0.003115, which we put in its respective place. That's the coordinate of a mammogram positive and a breast cancer. And since we have also this information that is about 0.35% of women over 40 will develop breast cancer, this is our marginal probability of H. So this and this will sum out up 0.0035. And since in every contingency table the result must be 1, then the rest is 0.9961. We do the same for the next conditional probability by saying the probability of D given H prime equals the joint probability of D and H prime divided by the probability of H prime. We do the math and we get the joint probability of D and H prime, which is in this case, this is the coordinate, that is the mammogram positive and no breast cancer, or H prime is 0.69755. Now we are in the position to fill out the rest of the places in our contingency table like that. And once we have all numbers in our contingency table, we are able to explore all possible conditional probabilities derived from this matrix. And we begin by saying the probability of D given H is 0.89. The probability of D given H prime is 0.07. The probability of D prime given H is 0.11, and the probability of D prime given H prime is 0.93. We continue, but now we begin and we say the probability of H given D is equal to 0.0427. The probability of H given D prime is 0.000415. The probability of H prime given D is 0.9572, and the probability of H prime given D prime is 0.999. Now, we put together all the probabilities that we have calculated using the matrix we have in the slide, and we come back to the question. The question says, if we tested a random woman over 40 for breast cancer using a mammogram and the test came back positive, that is, the test suggested that the patient has cancer, what is the probability that the patient actually has breast cancer, or the probability of H given D? Now, we have a wide number of possibilities, so we just have to look what we are looking for. And it seems that we found the answer. The probability of H given D equals 0.0427. Now we continue with our analysis. Since, we take the probability of D given H is 0.89, but the probability the other way around of H given D is 0.0427. What these probabilities have in common is the numerator. So if the numerator, that is the joint probability of D and H, or H and D, is the same, we can use the equivalence to say that the probability of D given H multiplied by the probability of H equals the probability of H given D multiplied by the probability of D. We have these numbers, and we will calculate the probability of H given D. So by doing some changes in the equation, we come to the probability of H given D equals the conditional probability of D given H multiplied by the probability of H divided by the probability of D. You see that the probability of H is 0.0035. The conditional probability is 0.89, and the marginal probability of D is, like we can identify here, 0.07287, which equals the 0.0427. Now, we have another form of the Bayesian theorem, which looks a little bit more complicated, but we are in the position to use it. So we take this form of the Bayes theorem, and we have already these numbers. The probability of D given H multiplied by the probability of H, that is 0.89 multiplied by 0.0035. This is the numerator, and if we see the formula, the numerator comes also in the denominator. So these numbers repeat in these numbers in the numerator will be repeated in the denominator. But now we have two expressions that we don't have in our calculations hitherto. So, but we have done so many or all possible conditional probabilities that we only have to take a look at one of them that fits. And this is the one we are looking for. The probability of D given H prima is 0.0699. And the conditional or the marginal probability of H prima, which is no breast cancer, is easy to identify, is 0.9965. So now we have all the numbers in our formula, so we can make the calculations, and our result is 0.0427. Now, we are in a position to use the Bayesian calculator. We go to the Bayesian calculator, and the Bayesian calculator asks us for the prior probability. The prior probability is this one, is 0.0035. So we give it 0.0035. The conditional probability is this 0.89. That is 0.89. And this one, this is the probability that the formula is asking for, 0.0699. 0.06999. So we give that, we click that, and the result is 0.0427. So if we tested a random woman over 40 for breast cancer using a mammogram, and the test came back positive, that is, the test suggested that the patient has cancer, the probability that the patient actually has breast cancer is 4.27. So if you liked this video, or if you think this video helped you, give me a like, and I will be glad to work with you the next problem with the Bayesian calculator. Bye.